Hello, hello. Today we're going to be taking on some tutorials on Solana. It's made by Paul X, which was recommended to me by some of the Solana um, community members here in the Philippines. So we're going to be taking on this tutorial, which teaches us how to build an escrow program, as an example. So let's go check that out. Yeah. There we go. Okay. Let's get to it. Let's get reading. Just open up another screen here just so I can see any messages. I'm not seeing the chat messages if ever, but I'll go open these ones up. Okay, let's just get started with it. Yeah, so I'm monitoring the chat on Twitch, but I can't see the ones on YouTube. So restream's being a little funky, but okay. So programming on Solana, an introduction. So we'll just go read through it and try to make sense of what we understand from it. Okay, so this guide is meant to serve as an intro in coding on Solana blockchain. SPL token UI. Ooh, I haven't heard of this before. Okay, let's read it later. Yeah, so we've gone through some of the Solana docs, minting your own tokens, and playing around with Anchor and a tic-tac-toe program. But let's see how to build an escrow following this guide. So, okay. I'm also like paying attention to how he's doing his blog posts because it's quite interesting. Okay, we'll make it a little bigger. Make it easier to read. Okay. An escrow smart contract is a good example to look at and build. So someone gives an asset, someone gives the payment, and then the escrow does the exchange, right? That's the escrow program. That's clear. A deadlock will be reached where no party wants to send their assets first. The traditional way is, the escrow agent releases both assets. Okay. So instead of having an escrow person, have the blockchain do it. Smart contracts, excellent. So that's what an escrow program is. Okay. So we're gonna start off with setting up the project following a certain template. So there's a GitHub setup template, uses template. Minimal Solana BPF program template. Okay, use this template. create a new repository. We'll do it under this one. We'll call it polxdev escrow sample tutorial. Okay. Okay. So we'll go pull this code. Let's probably do it here. Projects, GitHub, git clone. Hi. We have our program set up. Let's go back to the tutorial. Use this template, we cloned it. You'll need Rust, we already have Rust. Solana, we already have it. If you don't know how to test Solana programs, remove all the testing code. Testing programs is a topic for another blog post. Remove the testing code in lib.rs. Let's go open that up. I think this is the... I forgot what these terminologies are. I think this is it an attribute? A trait? I forgot what it was called. Oh, I have my notes, so I can probably open my notes. That's why I write down notes. So... Rust. ELI5 docs. And then I would open up definitions. So traits are shared behaviors you want to share, right? So it's not traits. Attributes are metadata. Hi, so these are attributes. So this is an attribute for this module, I guess. Okay, let's go back. Just have to refresh ourselves. Oh, hi. If you don't know how to test Solana programs yet, remove all the testing code, testing, blah, blah, blah. Lastly, remove testing dependencies. So we'll remove this one. All of these testing stuff. And then we'll go to cargo and remove all the dependencies for testing. I think this one. I don't know if this one should be removed. I'm not sure. I'm not familiar with this one. So let's remove it as well. Let's remove it. It should now look like this. Solana escrow. Let's put that as Solana escrow. Dependencies, Solana program 1.94, and then the lib. So we'll remove all of these dev dependencies. Okay. Have a look into lib.rs. First required traits. You know what? Instead of like repeatedly opening it, let's just have this one here. Oh, hi. So have a look into lib.rs. First, the required crates are brought into scope using use, right? So these are the things that we'll be using from the Solana program. Count info, entry point, program result, and pub key. So this is I'm not used to this way of importing stuff, so I'm gonna write that down here. Let's open up discoveries. How to import crates or dependencies. Code below appears to import the specified classes. Count info, program result, pub key. So that they don't need namespacing upon usage. Okay. Just making notes where we can. Okay. Then we use the entry point macro to declare the process instruction function, the entry point. So I think this entry point is in the Solana program. So this is the entry point for the Solana program. Process instruction. Okay. Oh, the entry point is the function called process instruction. Process instruction is defined to be this one, having these parameters. Entry points are the only way to call a program. All calls through the function declared. All calls go through the function declared as the entry point. When called, a program is passed to its BPF loader, which processes the call. Different BPF loaders may require different entry points. Okay, so as I understand it, BPF is Berkeley Packet Filter. It's like a secure way of programming. I am not familiar with different kinds of BPF loaders, and I'm not entirely sure which part here is the BPF loader. I think this one defines one way of actually defining the entry point. Okay. So the reason for the existence of multiple BPF loaders is that it itself is a program. If updates are made to the program, a new program version has to be deployed. We can see that the BPF loader we are using requires the entry point function to take 3 arguments: program ID, accounts, instructions. Why you'd want to access it inside the program will become apparent later. Instruction data is data passed to the program by the caller. It could be anything. Finally, to understand what accounts are, we need to dive deeper into the Solana programming model. So we already took up discussion about what Solana accounts are in a previous live stream. So I'll probably link it here later. Solana programs are stateless. If you want to store states, use accounts. Programs themselves are stored in accounts which are marked executable. Each account can hold data and Solana. Each account also has an owner, and only the owner may debit the account and adjust its data. Crediting may be done by anyone. Here's an example of an account. As you can see in the example account, it has its owner field set to the system program. As a matter of fact, accounts can only be owned by programs. Now you might think, does that mean that my own Solana account is actually not owned by myself? Yes, because it's owned by the system program, right? Remember, they are stored in accounts, and these are executable accounts. Even programs are owned by programs. Remember, they are stored in accounts, and these executable accounts are owned by the BPF loader. So programs are executable accounts, and accounts are just the storage mechanism. Okay. They are owned by the native loader and have special privileges, allocating memory, marking accounts as executables. Yeah. If you look at the system program, you'll see although the program owns all basic Solana accounts, it can only transfer Solana from an account where the transaction has been signed by the private key of the Solana account being debited. In theory, programs have full autonomy over the accounts they own. It is up to the program's creator to limit this autonomy, and up to the users of the program to verify the program's creator has really done so. We'll get to how a program can check whether a transaction has been signed and how a program becomes the owner of an account in a bit. Before we conclude the entry point section, there's one more thing to know. All accounts to be read or written to must be passed into the entry point function. Okay. This allows the runtime to parallelize transactions. If the runtime knows all the accounts that will be written to and read by everyone at all times, it can run those transactions in parallel that do not touch the same accounts or touch the same accounts but only read and don't write. Okay. If a transaction violates this constraint and reads or writes to an account of which the runtime has not been notified, the transaction will fail. Okay, so it's for parallelism purposes. So this accounts apparently specifies all the accounts that must be read or written to. Okay. Conclude the session, create a new entry point, .rs. Okay. Next to lib.rs, move lib.rs code there. Okay. Copied it. And move, finally register entry point module inside lib.rs. Pub mod entry point. Okay. So I'm not sure what this means. Organizes codes into modules. Oh, thank God for tooltips. Use mod to create new modules to encapsulate code, including other modules. Mod foo, bar, type, etc. So it's like a namespace or a module, right? It's modularization purposes. Okay, like struct and denom module, and its contents are private by default, inaccessible to code outside of the module. To learn more about allowing access, see the documentation for pub. I think pub just means public module, entry point. Theory recap, each program is processed by its BPF loader. Accounts are used to store state. Accounts are owned by programs. Only an account owner may debit an account and adjust its data. All accounts to be written to or read must be passed into the entry point. Instruction.rs, part 1. General code structure in the beginning of the escrow program flow. Code structure. Next, create a file instruction.rs. Okay, let's do that. Next to the other two and register inside librs like you did with the entry point. So does that mean just like the entry point? So we'll say instruction. Okay. To understand the new file's purpose, let's look at the common way to structure a program's code and the way we will structure our program as well. Lib.rs, registering the modules, entry point.rs, entry point to the program, instruction.rs, program API deserializing or serializing instruction data, processor. Alright, so I'll go ahead and write these files down. Okay, processor.rs, state.rs, error.rs. Then we have some get ignores, cargoes, licenses. Flow of the program, someone calls the entry point. Okay. The entry point forwards arguments to the processor. Processor asks instruction RS to decode the instruction data. Okay, makes sense. Because again, the data parameter is defined as like instruction data is like just byte data, right? So it needs to be interpreted. So the processor asks the instruction how to interpret it. Then using the decoded data, the processor will now decide which processing function to use to process the request. The processor may use state.rs to encode state into or decode the state. So state encoding or decoding is state, which has been passed into the entry point. As you can see, instruction.rs defines the API of the program. While there is only one entry point, program execution can follow different paths depending on the given instruction data that is decoded inside instruction.rs. Again, because the parameter for the instructions can be, we have byte data. So we can like specify a lot of instructions or a lot of space for data. And that's bounded by the byte data. Okay. Beginning of the escrow program flow. Let's now look at the different execution paths our programs may take by zooming out and sketching the program flow for our escrow program. Remember, we have two parties, Alice and Bob. So there are two system program accounts. Right. So this means that there are two people who have two different wallets. Because Alice and Bob wants to transfer tokens, will make use of, you guessed it, the token program. In the token program, to hold the token, you need a token account. Okay. Alice and Bob need an account for each token, so we get 4 more accounts. So the token program will hold the token, and then Alice and Bob need an account for themselves, because one of them will be where they will put their tokens. One of them will be for where they will receive the token. So I'll call our tokens X and token Y. So Alice gets an X and the Y account, and so does Bob, right? Our own tokens are X and Y, but this escrow will work for any tokens on Solana, USDC, SRM. Since escrow creation and the trade won't happen inside a single transaction, it's probably a good idea to have another account to save some escrow data. Example, store how much of token Y Alice wants in exchange for her token X, but we'll get to that later. Okay, let's just ride it along, even if things may not exactly make sense. Note that this account is created for each exchange. For now, our world looks like this. There's an escrow program which owns the escrow state account. So this holds the state data, right? It's just held in an account. Then we have the system program which owns the accounts, the Solana accounts of Alice and Bob. And then we're defining our own token program, which is also owned by, I think, the system program that has these accounts for Alice. Token X, token Y, token X, token Y for Bob. Now there are two questions you might ask. How will Alice and Bob transfer ownership of X and Y to the escrow respectively from their main accounts, as I understand it? And how are their main accounts connected to their token accounts? To find answers to these questions, we must briefly jump into the token program. Token program. The naive way one might connect Alice's main account to her token accounts is by not connecting them at all. Whenever she wanted to transfer a token, she'd use the private key of the token account. Not sustainable if Alice owned many tokens, because that would require her to keep a private key for each token. Makes sense. Much easier if Alice just had one private key for all her token accounts, and this is exactly how the token program does it. It assigns each token account an owner. Note that this token account owner attribute is not the same as the account owner. Right, because the account owner is the token program. The account owner is an internal Solana attribute that will always be a program. Right, the token program. The new token owner attribute is something the token program declares in the user space or the application space, right? The program that we are building. It's encoded inside the token account's data. So I think it's this one maybe, or the data inside the account, in addition to other properties. So we can read about this later, such as the balance of the tokens that the accounts hold. I will call the token owner authority, and the Solana internal owner in the rest of the post to avoid confusion. Makes sense. The existence of the authority also means that once a token account has been set up, its private key is useless. Only its authority matters. And the authority is going to be some other address, in our case, Alice and Bob's main account. So these things have authorities which point to their main accounts. Okay. When making a token transfer, they simply have to sign the transaction with the private key of their main account. All internal Solana internal account information are saved into the fields on the account, but never into the data field, which is meant solely for user space information. So it's on the fields on the account, but not into the data. Okay. So an account has data, and then this is the things that you can modify as the owner or the authority, but not modifiable by programs or applications. The key, the signer, the writable, the owner of an account, right? Whether it's executable or not, and details about its thread. You can see all of this when we look at the token account in the Explorer. It parses the account's data property and displays its user space field formatted properly. You'll probably notice the mint field in the Explorer. This is how we know which token the token account belongs to. So let's go check it out, what he might be referring to. So there's a mint field. This is how we know which token the token account belongs to. So we're going to be defining our own token, as I understand it. So that's what it would be pointing to. Okay. This is how we know for each token there is one mint account that holds the token's metadata, such as the supply. Right. So this is the mint account. So if you go to USDT, this is saying how much it's showing the volume of the market movements and the current supply. Okay. We'll need this field later to verify that the token accounts Alice and Bob use really belong to asset X and Y, and that neither party is sneaking in a wrong asset. So the mint field, which is a property of that token account, is what we'll use to make sure that they are indeed using tokens X and Y, and you're not just swapping in, you know, something worthless like Bitcoin. I'm kidding. We'll need this field later. Okay. With all this in mind, we can populate our world with more information. So owned by the token program, token. Owned by the escrow program, something that holds on the state. Owned by the system program, it's the accounts, right? Accounts of the individuals. For simplicity's sake, I've removed the programs and their arrows and simply colored the accounts. Once again, the owned by arrows in the diagram are referring to user space ownership, not the internal Solana account ownership. right? The authority or the owner, right? This is talking about authority. Now we know how all these accounts are connected, but we don't know yet how Alice can transfer tokens to the escrow. We'll cover this now. Transferring ownership. The only way to own units of a token is to own a token account that holds some token balance of the token referenced by the account's user space mint property. That was a mouthful, so let's read it again. The only way to own units of a token, so if I want to own Solana or GRT or USDT, is to own a token account that holds some token balance. So he's saying that you need to have an account under that token, right? So if there's this program, you need to have an account under that program, and that's how you have an account under that token. That's what he's saying. To own a token, you must have a token account that holds some balance of that token as specified in that mint property. Hence, the escrow program will need an account to hold Alice's X token. That's why they're creating Alice's token X, right? One way of achieving this is to have Alice create a temporary X token account to which she transfers the X token she wants to trade. So a temporary token is created. Okay. So this is the token account, right? Mint X. Right. This is the token accounts. And then Alice has her own, wallet containing her tokens for X. But then if she's gonna do the escrow process, she needs to have like another account, which is marked as temporarily owned, where she can put her assets first as the first step of the escrow. Alice creates a temporary X token to which she transfers the X token she wants to trade. The token program sets no limits on how many tokens for many tokens for the same mint one may be the authority of. So meaning you can have multiple accounts. You can have multiple wallets under the same token. Then, using a function in the token program, she transfers the authority of the temporary X token account to the escrow program using a function in the token program. So she created her account, right? She created her account. She uses the token account program, which has a function to transfer balances from accounts within that token to their temporary account, to their temporary token. And yeah. And she transfers the authority. So she changes who has the authority for this token to the temporary X token account. So this guy now owns this temporary token. So let's add the temporary account to our escrow world. The image shows the escrow world before Alice transfers token accounts to the ownership. So she put money in and then says, okay, escrow guy, hold on to it. Like that's what happened. Okay, there's one problem here. What exactly does Alice transfer ownership to? Enter program derived addresses, PDAs. So I've seen these terminologies before, PDAs, but I haven't completely understood it. So let's read it together. Okay, they're gonna go into explaining it, but let's look at the things that we recapped. Use the data field to save user data, application data in the data field. The token program owns token accounts, which inside their data field holds the relevant information. The token program also owns token mint accounts with relevant data. So mint accounts are like, USDT and etc. Each token account holds a reference to their token mint account. So if I have a wallet under USDT, they have a reference to what their mint account was. So that's where that wallet belongs to. The token program allows the authority of a token account, meaning not the Solana program owner, but the owner of the wallet or the account, allows the authority of the token account to transfer its ownership to another address, like what we're going to be doing here. I put some money, and then escrow account here, take authority of it. So I guess that's why they call it authority, not exactly owner, because this guy, Alice, is actually the person who really owns it, but they hand over the authority to the escrow account. All internal Solana internal account information are saved into fields on the account, but never into the data field, which is solely meant for user space information. Yep, okay. PDAs. We'd like some way for the program to own the X tokens while the escrow is open and waiting for Bob's transaction. Question then is, can programs be made the authority of a token account? Well, no, but actually yes. The trick is to assign the token account authority to a program-derived address of the escrow program. For now, it is enough for you to know this address exists, and we can use it to let the program sign transactions to make it authority of token accounts. As I remember, if from how I studied program-derived addresses, and I have like 15-25% confidence here, program-derived addresses are they are accounts owned by a certain program that is like generated from another thing or derived from another thing. So that might be the token that it wants signing to. So I think, okay, so this is my guess, which can be wrong. So given this diagram, Alice created a temporary token account under the X token, right? And since I am the owner of this account, I can use a function under some system program to derive addresses based on my ownership of this account. And because I can sign it, because I really do own this, then I am granting access to this this program to sign things in my behalf. I think that's how it works. But that's a guess. Let's see if that actually is true. We'll cover PDAs in depth, but for now, let's go back into coding. Actually, I'm curious. Actually, want to see whether that is correct. Allow programmatically generated signatures to be used when calling between programs. Using a program-derived address, a program may be given the authority over an account and later transfer that authority to another. This is possible because the program can act as the signer in the transaction that gives authority. For example, two users want to make a wager on the outcome of a game in Solana. They must each transfer their wager's assets to some intermediary, the escrow. Currently, there is no way to implement this intermediary as a program in Solana because the intermediary program cannot transfer the assets to the winner. This capability is necessary for many DeFi applications since it requires assets to be transferred to an escrow agent until some event occurs that determines the new owner. Decentralized exchanges that transfer assets, etc., etc. Examples. Program-derived addresses allow programs to control specific addresses, right? So I'm an owner. There's this program, and I want to derive an address that I am granting authority to. Allow programs to control specific addresses called program addresses. So they are addresses under a certain program, like an escrow program, in such a way that no external user can generate valid transactions with the signatures for those addresses. So they are owned by that program. Nobody else can work on it or use it. Allow programs to programmatically sign for program addresses that are present in instructions invoked by cross-program invocations. Okay, not everything's making sense. Given the two conditions, user can securely transfer or assign authority of on-chain assets, right? So on-chain assets, things that I own, assign authority to program addresses. And the programs can then assign the authority elsewhere at its discretion based on, how the program's developed or designed. Okay. I wouldn't exactly say that's 100%, correct for me, but like I'm getting the gist of it. We left off at instruction.rs with the knowledge that this file would define the API of the program, but without having written any code yet. Let's start coding by adding an init escrow API endpoint. So open it up. Let's go read it. Starts the trade by creating and populating an escrow account and transferring the ownership of the given token to the PDA. Accounts expected. The signer, the account of the person initializing escrow, the writable, temporary token account that should be created prior to this instruction and owned by the initializer. Empty array, the initializer's token account for the token they will receive should the trade go through. So if I want to receive Ethereum, I should receive Ethereum. So this is the token account. Writable, the escrow account. It will hold all necessary information about the trade, the rent sysvar, the token program. Okay. Although it does not touch accounts, it is helpful to define which accounts you expect here, so all the required calling info is in one place and easy to find for others. Additionally, it's helpful to add required account properties inside brackets. So these are all parameters, but this must be the signer, this must be writable, etc. Note that everything is a comment, no effect on the program. Documentation, writable property should remind you of the parallelization I explained above. These are write. If the caller does not mark the account writable in their calling code, but the program attempts to write to it, the transaction will fail. Let me explain why the endpoint looks like this. We need account 0, and specifically account 0 as the signer, because transferring the ownership of the temporary account requires the initiator signature. I'll be referring to Alice as the initializer and Bob as the taker in the code. Alice initiates the escrow, Bob takes the trade. Please let me know if you can come up with better naming. Account 1 is a temporary token X which needs to be writable. This is because changing token account ownership is a user space change, which means the data field of the account will be changed. So it needs to be writable. Account 2 is Alice's token Y account, the thing that they'll receive from. While it will be written to eventually, it won't happen in this transaction, which is why we can leave the brackets empty. So it's empty, so it's read-only. Account 3 is the escrow account, which also needs to be writable because the program will write escrow information onto it. Account 4 is the rent sysvar. I'll explain this detail once we get to writing the processor code. What you should remember for now is that account 5 is the account of the token program itself. I will explain why we need this account as well when we get to writing the processor code. Solana has sysvars that are parameters of the Solana cluster you are on. These sysvars can be accessed through accounts and store parameters such as what the current fee or rent is. As of Solana program at this version, sysvars can also be accessed without being passed into the entry point as an account. So, so apparently this might not be necessary anymore since there have been updates on the Solana program. Okay. Finally, the program requires an amount of token Y that Alice wants to receive for her X tokens. This amount is not provided through an account, but through instruction data. Instruction.rs is responsible for decoding instruction data, so that's what we'll do next. So let's go to this section, and we'll just copy it and then read it together. I feel like this should be over here. Oh, it's a duplicate, so I'm just gonna delete this one. There appears to be something wrong with the import. Use create error. A similar path exists. Standard error. Original diagnostic. Failed to resolve. Unresolved import. Unresolved import. A similar path exists. Standard error. Okay. Let's go see what this means. Because I feel like this is just an old tutorial, and the standard library might have changed already. I think this is standard. I'm not entirely sure. Okay, let's just read the instructions first, see if we can figure things out later. Instruction.rs is responsible for decoding the instruction data, so that's what we'll do next. Okay, so it implemented something. Unpack. Function unpack expects a reference to a slice of U8. Unpack expects a reference, right? Address of, to a slice, brackets, of U8. So byte. It looks at the first byte. Okay. To determine how to decode using match the rest of the slice. Okay, so let's read a little bit of Rust, see if we can piece things together here. So the escrow instruction has an implementation. It has a public function called unpack, which has a parameter for a reference to a slice of a byte, which returns itself and the program error. So what it does first is it receives the input and it splits the first entry. So returns the first and all of the rest of the elements of the slice, or none if it is empty. So if it's this one, then it would get 0, and then it would get 1 or 2. So it splits or okay or an error. This is an option. And if it fails, then it's gonna fail, and then it's gonna say invalid instruction. That's why we wanna like define this invalid instruction is. So let's go search this. Solana. Solana invalid instruction. Escrow error. I'm not entirely sure if this was made, this error is made by the tutorial themselves or if it is. It also uses this example. I think, is this still Paul? It says Jim. I hope this wasn't lifted by somebody else's, but okay. Let's go back. Okay. So if there's an error, then we have that as tag rest. Okay, match. Tag. So if the first byte is 0, then we are returning an init escrow enum with the amount equal to unpacking the amount given the rest of the input. Right. Okay. And then to unpack the amount from a slice of data, so we use the first byte to determine if its type is, if the first byte is completely empty, like 0. Okay. So we get the remaining slice, and then the amount is equal to the input, the remaining slice. We get everything. We get 8. I'm not familiar with this. Return a reference to the element, to an element or sub-slice, depending on the type of the index. If given a position, returns a reference to the element at that position. Okay. Or none if out of bounds. If given a range, return the subsize corresponding to that range, or none if out of bounds. So if you have 10, 40, 30, I'm unfamiliar with this. I'm not sure what's going on here. v.get from 0 to 2 not exclusive gets a 0 and 1, which is 10 and 40. But what does this mean? I don't understand what this means. It should be none. It should be none. Okay. Okay. So this gets possibly a slice of 8 bytes. A slice of 8 bytes. And then returns none if the option is none, otherwise calls f with the wrapped value and returns the result. Some language call this operation flat map. Oh, okay. Okay. And then we have the slice. Oh, so this is how you do anonymous functions? You wrap it with brackets, I mean with bars, and then you just say what happens next. There's no arrows. So this is the parameter slice, and then what we're gonna do is slice dot try into. Okay. Try into. Conversion. What conversion is it trying to do? This gets us a slice of byte data. And then, once we have that slice of byte data, we try to turn that slice of byte data into a slice of byte data, which it then tries to map. Create a native endian integer value from its representation as a byte array in little endian. When starting from a slice rather than an array, fallible conversion APIs can be used. Okay. Very not familiar about these things. Then if everything's okay, then it's great. You have the amount. Otherwise, it's an invalid instruction. Then that's your return. Okay. Okay. Not everything makes sense, but okay. Unpack expects a reference to a slice. It looks like the first byte. Determines how to decode using match. For now, we'll leave it at one instruction during instruction where Bob takes the trade. Unpack amount decodes the rest to get a unsigned integer with 64 bits representing the amount. You can look up the individual functions yourself. What's most important for now is that you understand what is going on at the high level in the unpack function. Choose which instruction. The first one is choose which instruction to build. Number 2, build and return that instruction. So I think it's this one, right? This is saying what instruction needs to be performed. Oh, I need to initialize the escrow. This one compiled because we're using an undefined error. Let's add that error next. Okay, so it was indeed part of it. Okay, cool. Solana has these bars that are parameters of Solana. Okay, create a new file, error.rs. Error.rs. Okay, we already have it. And add the following to your cargo toml. Go back to error. And say use this error. Derive. Error, debug, copy, clone. So I'm intentionally writing it down manually just so I get familiar with the movements. Okay. What we're doing here is defining an error type. Instead of having to write the format display implementation ourselves, as is done in the example, the link points to, we use the handy this error library that does it for us using the hashtag error metadata notation or attribute notation. This will become especially useful when we add more errors later on. Looking back into the instruction.rs, we can see that we are not quite done. The compiler is telling us it has no way of turning escrow error into a program error. The trait standard convert from error is not implemented for Solana program. So let's implement away. So inside error.rs, we're gonna say use Solana program error, and then define an implementation from escrow error for program error. Okay. Let's stop for a moment to understand what is happening here. We are implementing a generic trait, specifically the from trait, which the question mark operator wants to use. To implement this trait, we have to implement the from function, which carries out the conversion. The program error enum, defined by the Solana program, provides a custom variant that allows us to convert from our program's escrow error to a program error. The reason we do this conversion in the first place is that the entry point returns a result of either nothing or a program error. Let's go back to entry point. A program result is a result of nothing or a program error. So public function for process. After creating the entry point, an init escrow endpoint, and our first error, we can finally move on to code processor.rs. This is where the magic happens. Start by creating processor.rs and registering it inside lib.rs. Then paste the following. So we put processor. Still having an error here. Okay. After creating the entry point and init and our first, we can finally move on to processor. Okay. This is where the magic happens. Start by creating and registering. Okay. Then paste the following into. Okay. So let's go ahead and just paste it. Okay. Let's start unpacking what's happening. First, we pass the reference to the slice, holding the instruction data. First, we pass the reference to the slice. Holding the instruction data. Reference to the slice to unpack it, right? And then we get the instruction. Then depending on the instruction you created earlier, note the question mark after the function call. So there's a question mark used in question mark to decide the operator should produce a value or propagate the value back to the caller. Okay. Okay. And then we do a switch on that instruction if the case is an init escrow with the amount of the amount, and then we say here's the message and then process the escrow. Okay. Message logs where we're going. Who defined this? Oh, it's Solana. Solana has message. Okay. Function process init escrow. To be cleared out, that just means there's other stuff around the code you're seeing. Don't copy those. Excuse me. So we have process, and then we are implementing this one. Okay. Process init escrow is next. To be clear, blah, 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 blah. Copy and replace your current use Solana program with the one here, or add the individual missing pieces. Inside process init escrow, we first create an iterator of accounts. This one. Okay. It is a mutable accounts iterator from that slice, from that reference to that slice. Needs to be mutable so we can take elements out of it. The first account we expect, as defined in instruction.rs, is the escrow's initializer, Alice's main account. That's the initializer. Next account info. That's not defined yet. She needs to be a signer, which we check right away. It's just a Boolean field on account info. Initializer, so they added this section, so we'll put that there. Program errors missing. I feel like I missed certain. There we go. Yeah. Okay. So you have the pub key and then account info. We need to import both next account info. There we go. And then we need SPL token. Da. Sino to? What's this? Failed to resolve use of undeclared crate or module SPL token. Who's this? Where's create an iterator for accounts? Add the highlighted lines. She needs to be signer right away. It's just a Boolean field, otherwise missing required signature. Okay. Next, add the highlighted lines. The temporary token account needs to be writable, but there is no need to explicitly check this. The transaction will fail automatically should Alice not mark the account as writable. You might ask yourself, why do we check that the token to receive account is actually owned by the token program, but don't do the same for temp token account? The answer is that later on in the function, we will ask the token program to transfer ownership of the temp token account to the program-derived address. This transfer will fail if the temp token account is not owned by the token program. Because as I'm sure you remember, only programs that own accounts may change accounts. Hence, there's no need for us to add another check here. Programs that own accounts may change accounts. Does that make sense? Programs that own accounts may mutate those accounts. Programs, you can only change accounts that you own, right? We don't make any changes to the token to receive account, though inside Alice. We don't make any changes to the token to receive account, though, inside Alice's transaction. We will just save it into the escrow data so that when Bob takes the trade, the escrow will know where to send asset Y. It's just the destination. Thus, for this account, we should add a check. So that token to receive account should indeed match the token ID. Note that nothing terrible would happen if we didn't. Instead of Alice's transaction failing because of our added check, Bob's would fail because the token program will attempt to send the Y tokens to Alice, but not be the authority of the token to receive account. That said, it seems more reasonable to let the transaction fail that actually led to the invalid state. Finally, I'm sure you have noticed that we're using a crate here, which we have not registered inside cargo.toml. So let's do that right now. See, it's challenging to go through these tutorials because errors really trigger me, and it's hard to like move past them until I figure them out. But that's a skill I gotta have, just to let things be a mess till they make sense later. Okay. Okay. We are using slightly different ways to import a dependency here than we did the other dependencies. That's because we are importing another Solana program that has its own entry point. but our program should only have one entry point, the one we defined earlier. Luckily, the token program provides a switch to turn its entry point off with the help of a cargo feature. Ooh, I haven't heard of this. This is something I need to study. Okay. Cargo features. Reference. Right? Okay. Back to our instructions. Processor. If you cannot or don't want to figure it out on your own, you can take a look into the escrow program that I created. Now back to processor.rs. Copy and replace the Solana program use statement and add more code to process init escrow. So let's go back to processor. Let's double check the imports. Account info, next account info, entry point program result, program errors there. Let's just make it consistent. Message, pub key, then it has these things. Okay, program pack is initialized. Sysvar rent, then sysvar. Okay. And then inside process init escrow, let temp token be this guy, and then we added these sections. So let's go put that in. Escrow error. Did we miss something? I'm not sure. Let's read. Now we see the rent sysvar in action. Let me explain. Rent is deducted from an account's balance according to their space requirements, i.e. the space an account and its fields take up in memory regularly. An account can, however, be made rent exempt if its balance is higher than some threshold that depends on the space it's consuming. Most of the time, you want your accounts to be rent exempt because once their balance goes to zero, they disappear. Also, make sure to add the new error variant inside error.rs and adjust the use of the statement. In this one, let's go back to error.rs. I don't recall we added something like this here before. Okay, I'm not sure this is exactly right. But let's put that there. Doesn't know what escrow error is. Ah, I see. I think I need to add this here. From this one. There we go. So this is how you import things from yourself, I guess. And then I think this one should also have errors or error so that it can actually properly get this one. Okay. And then now it knows what error is because we registered on the library. Okay. Makes sense. Excellent. Okay. Let's hide this one. Let's read this one. Another unfamiliar thing is happening here. For the first time, we're accessing the data field. Because data is just an array of unsigned integer, we need to deserialize it with escrow unpack unchecked. This is a function inside state.rs, which we will create in the next section. Next section. Okay. Let's keep going. Create state.rs and register it inside lib.rs. The state file is responsible for defining state objects that the processor can use, serializing and deserializing such objects from and into the arrays of unsigned 8 respectively. Start by adding the following to state.rs. So let's go to state.rs, let's copy it, slap it on here. We need to save temp token account pub key so that when Bob takes the trade, the escrow program can send tokens from the account at that location to Bob's account. We already know that Bob will have to pass in the account into his entry point call eventually, so why do we save it here? First, if we save its public key here, Bob can easily find the address of the accounts he needs to pass into the entry point. Otherwise, Alice would have to send him not only the escrow account address, but also her account addresses. Secondly, and more important for security, is that Bob could pass in a different token account. Nothing stops him from doing so if we don't add a check requiring him to pass in the account with temp token account pub key as its public key. And to add that check later in the processor, we need the init escrow instruction to save the temp token account pub key. When writing Solana programs, be mindful of the fact that any accounts may be passed into the entry point, including different ones than those defined in the API inside instruction.rs. So people can just, plug in whatever accounts. So it's the program's responsibility to check that the received accounts is equal to the expected accounts. Initializer token to receive account pub key needs to be saved so that when Bob takes the trade, his tokens can be sent to that account. That's where he will be sending it to. Expected amount will be used to check that Bob sends enough of his tokens. That leaves initializer pub key and is initialized. I'll explain the latter now and the former later on. We use is initialized to determine whether a given escrow account is already in use. The serialization, deserialization are all standardized in the traits of the program pack module. First, implement sealed and is initialized. Okay, so we'll add this one. So we are expanding this one. Okay. Okay. Sealed is just Solana's version of Rust's sized trait. I also don't know what this is. Let's put that into things that we need to study. Rust sized trait source. I'll put it here. Things we'll read later on. Okay. State. Now pack, which relies on sealed, and in our case also on is initialized. I'm not sure about this sentence construction. It's a big but simple block of code. I'll split it into two parts. Let's start with the first one. You can copy and replace the use imports again. Okay, let's do that. So now we have pack, sealed, and these array references. So we're implementing packed for escrow. First requirement for something implementing pack is defining length, which is the size of our type. Looking at our escrow struct, we can see how to calculate the length of the struct by adding the size of the individual data types. 1 boolean, 3 public keys for accounts, and 1 64-bit. So yeah, it's a long, right? So this would be 3 times 32, 3 times 32, 96, 97 plus 8, 105. It's okay to use an entire U8 for the boolean, since it'll make our coding easier. The cost of those extra wasted bits is infinitesimal. After defining the escrow's length, we implement unpack from slice, which turns an array of unsigned integer into an instance of the escrow struct we defined above. So unpacking it from a slice of unsigned integers, a reference to a slice of unsigned integers, which returns itself and or a program error. So let's practice reading Rust. Okay, so this is the implementation of the pack trait for the escrow type or struct, and within that implementation we have a scoped variable length, which is a size of 105 bytes. Bytes or bits? Is this bits? I think that's bytes. No, it's bits. It's bits. Okay. Okay. So we get the source array reference from 0 to the length, and that, as I understand it, gets a portion of that slice of unsigned integers, and then the array references from the source, it cuts things up with 1 byte or 1 bit, 32 bits, 32 bits, 32 bits, and 8 bits, and this is mapped into is initialized, initializer, pub key, temp token, these parameters basically. Then is initialized is equal to matching of is initialized. If it's 0, it's false. If it's 1, it's true. Otherwise, it's invalid. And then the escrow data is the is initialized, initializer public key, and this is the pub key definition in Solana. So pub key from an array, initializer pub key, which is reference, and we want to get the value from it. Temp token account public key, same thing. Initialize token, again, they're all just from arrays, and we're just defining them as public keys. In the expected amount, we are getting an unsigned 64. It's an integer, a big long with 64 bits, with deriving that number from a little endian encoding for the expected amount. Okay, and then that unpacks it from the slice. Okay. Notable here is the use of arrayref, a library for getting references to sections of a slice. The docs should be enough to understand. Just 4 different. Make sure to add the library. Okay, let's do that. Fine. We can now deserialize state. Serialization is next. So this is unpack from slice. This is packed into slice. Okay. So let's practice reading now. Okay. So when you want to pack something into a slice, you need a reference to yourself and the destination slice of unsigned integers. Unsigned int, right? So the destination, we define the section necessary, which is just the length of the escrow, and then we from those parts what does this return actually? Oh, it doesn't return anything because it mutates the references directly. Okay, so from itself, on the destination, it defines the references, right? So it uses mutable array references because we're going to be mutating the array references there on that destination, and then we cut it up 132, 32, 32, 8. Get those variables from the escrow. We define these are all prepended with destinations. We get the values from ourselves, and then we just assign it. So is initialized of the first byte, I guess, or the first bit is equal to, or the first byte, yeah, it's unsigned 8. So the first byte is equal to the value at this reference as an unsigned integer. And then we copy these things. So initialize our destination, copy it from this slice as a reference, from this slice as a reference, reference, reference. And this one is equal to little endian bytes. Okay, clear. Sounds good. With state.rs done, let's go back to the processor.rs and adjust one of our use statements. From use crate, this one to this one, because we're adding the state escrow now. Okay. Processor part 2, PDAs part 2, CPIs part 1. Let's finish the process init escrow function by first adding the state serialization. We've already created the escrow struct instance and checked that it is indeed uninitialized. Time to populate the structs fields. So where is this? Process init escrow. It's in processor. So let mutable escrow is this one, and then it's adding this section. So let's read it. Okay. So the escrow information, it is initialized. The public key is the initializer's key. The temporary token account is defined by that temporary token that we received, and the initializer token to receive account is where they would like to receive it, and then how much. And then the escrow, we pack that data into an instruction. Try borrow mutable data. Escrow account. Okay. Pretty straightforward. Pack is another default function which internally calls our pack into slice function. Alright, so if we go here, go to definition, or we just go to state, escrow, then we look for pack. It implements the pack, right? So then it uses this, it uses the trait. Okay. PDA is part 2. There's one thing left to do inside process init escrow. Transferring user space ownership of the temporary token account to the PDA. This is a good time to explain what PDAs actually are and why we might need the program ID inside a process function. Copy and look at the highlighted line. So let's read it. So we pack the information and then we find the program address where the seeds is equal to I think this is how you define a string. So the address to I'm not sure. Let's read it. We create a PDA by passing in an array of seeds. So I think this is an array of seeds. It just has one seed value. It's called escrow. What does B string mean in Rust? Any string prefixed by B tells the compiler that the string should be treated as a byte sequence. Okay. So it's an array of byte sequences. And then this is the seed. And then seeds and then the program ID. Okay. We get back a new PDA and the bump seed. We won't need the bump seed we won't need the bump seed analysis transaction with a 1 over 2 raised to 255 chance the function fails. Big number. Okay. In our case, the seeds can be static. There are cases such as associated token account program where they aren't, because different users should own different associated token accounts. We just need one PDA that can own n temporary token accounts for different escrows occurring at any and possibly the same point in time. Okay, but what is a PDA? Normally, Solana key pairs use the ED25519. I haven't read this yet. Standard. This means normal public keys lie on the ED25519 elliptic curve. Elliptic curve, as I understand it, it uses ellipses. So the reason why ellipses are useful for cryptography is because ellipses are defined to be, they have two central focal points, and then the way that you draw a curve around the ellipse is the sum distance of any point on the ellipse is equal to any point on the ellipse is equal to each and every point on the ellipse is equal to each other, is equidistant to each other in relation to the sum of their distance from their focal points, right? So this is how I understand ellipse. So you have two focal points, F1 and F2, and if you draw any point from this point here to here, if you move it to a different point, the sum of those distances would be equal across the whole thing. And this is useful in cryptography because that means you can represent those focal points as your keys, right? Like you have a key, and the Solana program thing might have a key. So basically, only two points are the only things that can, like, if you know where the point is, then you're the only ones that can actually determine that kind of ellipse. But knowledge of that point is private, right? So that's how I understand it's used in the cryptography, but I'm pretty sure it's not accurately explained. Just general ideas that I can remember. PDAs are public keys that are derived from the program ID and the seeds as well as having been pushed off the curve by the bump seed. Oh, so this is the curve, the nonce derived public key. Program derived addresses do not lie on the ED25519 curve and therefore have no private key associated with them. A PDA is just a random array of bytes, with the only defining feature being that they are not on that curve. That said, they can still be used as normal addresses most of the time. You should absolutely read the different docs on PDAs. Okay, so we're gonna put that into our reading list. And if you guys want to join me in reading these, join me on my next streams. We don't use the bump seed here yet, also indicated by the underscore before the variable name. If we go back to processor, we see the bump seed underscore, it's unused. We will do that when we look into how it's possible to sign messages with PDAs even without a private key in the PDAs part 3 inside Bob transactions. Time check, it's 3:20. I'm going to be preparing to leave sometime around 4:15 maybe, so we have maybe an hour left to keep going. Okay. For now, let's look at how we can transfer the user space ownership of the temporary token account to the PDA. To do this, we will call the token program from our escrow program, which is called cross-program invocation, which I think is a unique property in Solana, I think. I'm not entirely sure. Executed using either invoke or the invoke signed function. Here we use invoke. In Bob's transactions, we will use the invoke signed. The difference will become clear then. Invoke takes two arguments, an instruction and an array of accounts. Okay. Use Solana program inside process. Okay, so they changed the import, so let's double check it. Program pack says var, it adds program invoke. Right. And then process init in escrow. I think this is what we add. Where is the OK? The OK is missing here. Ah, because we're adding up to here. Okay. Okay. So let's read what we added. So we defined the serialization and deserialization of our application. We initialized it, and then we packed it, and then we are now getting a PDA, program derived account. And then this is saying the token program is the next account in the account info iterator. Is that right? Let's see the instruction. The token program. That's excellent. Okay. So this is the token program, which is the next account. And then using Solana's, I can't remember what SPL means again. What was SPL? Programming language? Solana programming library. So using Solana programming library, token program, we use the instruction called set authority to set this token program. Using this token program, this own public key, we are now saying that the owner of this token account, temporary token account, is the PDA that we just generated, which is owned by that by our current program, the escrow program. And the token, it is now the account owner, authority type. It is now an account owner. So there's different authority types apparently. Ooh, okay. And then the owner's public key is the initializer's key, and the signer's public keys are these ones. I'm curious about why these are the data types. It's varying. This is a reference to a slice of pub key references. This is a reference to a pub key. So there can be multiple signers, I guess that's what it means. Multiple signatures. Okay. Calling the token program to transfer token account load ownership, it performs invoke. This is the instruction, owner change instruction. And then the account infos is the temporary token account, the initializer, and then the token program. It uses 3 parameters apparently, or 2 parameters, but has multiple account informations. Okay. It's a rule that the program being called through a CPI must include as an account in the second argument of invoke the program being called through a CPI. Okay. The token program has to be included. Next, we create the instruction. This is just the instruction that the token program would expect were we executing a normal call. The token program defines some helper functions inside its instruction.rs that we can make use of. Of particular interest to us is the set authority function, which is a builder function to create such an instruction. I think it's this one, right? You pass in the token program ID, then the account whose authority we'd like to change. The accounts, that's the new authority, in our case the PDA. The type of authority change, there are different authority types for token accounts. We care about changing the main authority. The current account authority, Alice, which is the initializer. And finally the public keys signing the CPI. The concept that is being used here is signature extension. In short, when including a signed account in a program call, in all CPIs, including that account made by that program inside the current instruction, the account will also be signed, i.e. the signature is extended to the CPIs. This is flying all over my head. Too many words. The concept that is being used here is signature extension. Okay, so this is CPIs and stuff, so that's why that's kind of overwhelming me. So I'm just gonna put this here as my next set of things to read. This isn't technically Rust, but this is more on Solana, right? PDA is more on Solana, right? So let's go back to our processor. In our case, this means that because Alice signed the init escrow transaction, the program can make the token program. The escrow program can make the token program set the authority CPI and include her public key as a signer public key. This is necessary because changing a token's account authority should of course require the approval of the current authority, which is Alice. Next to the instruction, we also need to pass in the accounts that are required by the instruction in addition to the accounts of the programs we are calling. You can look these up by going to these token programs instruction.rs and finding the set authority enum, whose comments will tell you which accounts are required. In our case, the current authority is account, the account whose authority is to be changed, and then the token program. Right, current authority is account. Okay, I kind of want to read about set authority, so let's check this out. It has a lot of parameters. Right. Okay. And then it would receive an instruction. No, it would result to an instruction. It produces an instruction, that's why this is an instruction. But performing the instruction, invoking it, I'm not entirely sure what defines these account infos. Who decides what should be included as an account info? Or where is these account information used? I'm not sure. Invoke signed. Account infos for check that the account reference cells are consistent with the request. For the account meta, in the instructions accounts, create an iterator for all of the accounts in the instruction, and then create an iterator in the account infos. If the account meta's public key is equal to this one, and it is writable, then borrow Lampert's and borrow data and then perform. Okay, I'm not entirely sure. That's enough as I can go. Okay. Note that before making a CPI, we should add another check that the token program is truly the account of the program. Otherwise, you might be calling a rogue program. If you're using the SPL token crate above version 3.1.1, which I do in this guide, you don't have to do this if you use their instruction builder functions, which is this one. They do it for you. Finally, adjust entry point.rs so that it looks like this. Use Solana. What's the last import? Pub key. Use crate processor. Entry point process instruction. And then we just do this one. Now you might be thinking, wait, we are giving the escrow program control over the temporary account, but Alice never transferred anything into it. Shouldn't that have happened before? And you're right, it should have happened before. But importantly, it does not have to happen inside the escrow program itself. We'll look into how she can make the transfer in the same transaction as the call to our program in the next section. So we're kind of like past midway, kind of getting a little tired, but we'll keep going. Trying out the program, understanding Alice's transaction. Because we've built a part of the program that is complete in itself, we can now try it out. In doing so, we can acquire knowledge about Solana. Example, where do accounts come from? I prepared 2 ways for you to interact with the program, and I encourage you to try them both. First, there is a set of scripts that test whether you implemented the program correctly. Reading them should also provide you with a better understanding of how we can interact with Solana programs on the client side. You can find the scripts and instructions on how to use them here. You can also use this UI to try out your program. Here's the code. It's a little more complex than just executing the scripts, but I explain how it works and what you need to do to make it work below. Feel free to build your own. Escrow UI. Okay, deploy your program on localnet. There are still some errors, so I'm just gonna double check what they are. State. We don't have state defined here, so that's good. Now it's saying escrow error. Escrow error does not have not rent exempt. So I can't remember if not rent exempt is defined here. So apparently they forgot to explain what this is. And then we're just gonna say not rent exempt, right? Go back to instructions. So they missed that part. We can tell them about that missing thing. Okay. Everything looks good now. Everything's not having issues. So let's follow the next set of instructions. Yep, we're done with this. We're done with this. Escrow UI. Okay. Deploying a program on localnet. Let's go. First, use the cargo build BPF. Hi. Let's just save our progress so far. Work in progress before deployment. Okay. First, use cargo BPF. Okay, cargo build BPF. To compile your program to a file with a SO file extension. What does it say? Failed to select a version for the requirement. Tom will edit. Candidate versions found which didn't match. Let's see our cargo. Require package proc macro crate. Huh. When did I use that? Because it requires Solana escrow version 0.1.0, which requires SPL token. So let's see what happens when we change this to 5. Let's put it back to what it was before. Run it again. What does it say? So it's saying I am getting 3.5.0, but it's unable to find failed to select. Oh, hi. So let's check out dependency issues relating to Toml edit. So it bumped Toml edit. At least this is a project that bumped it. Oh, hi. What's RTX? What is this project? Runtime executor. ASDF Rust clone. Let's go check their dependency for edit. He said 0.19. Not entirely sure if that's gonna work for us, but let's just see. Must have been a security patch. Failed to select a version for the required Toml edit 0.19.2. Failed to select a version for the requirement Toml edit 0.19.2. Candidate versions found. Maybe my cargo isn't updated, maybe. Yeah. Apparently, Cargo can sometimes get into a state where its local registry cache will corrupt itself and cargo won't be able to discover new versions of dependencies. So I'm gonna hide this now, right? Let's go back to what it was before. Cargo. To resolve this, delete the cargo registry folder and run the build command again. So let's do that. So rm-rf bravely cargo registry. Ooh, that took a while. It's taking a while. Okay. Okay. It's saying the same thing. Okay, candidate versions which didn't match. Let's just copy paste this one, see what happens when we search it. Tom will edit. The issue is caused by an outdated Solana version. Updating Solana to CLI. Okay, Solana version. How to update Solana CLI. Ooh, convenient. Okay, so that explains what that kind of problem is about. Okay, so it's done updating. Let's see if we can build it again. It's updating its BPF. Okay. Why to move? I'm just playing chess while waiting for the update. Okay. Okay. It's getting a little bright. Just gonna fix up my room a bit while we wait for the update. Okay, we're back. And we have updated our Solana, but it still cannot find a version for the requirement. Will edit. That's greater than 0.18. Candidate versions found. I feel like the crates are the ones that I need to update. Because it could be the indexes it has is not updated. Cargo dash update. I'm not sure. I'm not sure. Let's keep looking. You need to update your Rust toolchain to 1.6. I think this is something completely new. Because proc macro crate hasn't updated their stuff. Which is going to be preventing us from actually completing this tutorial. Okay. Let's see what happens when we try to set it like this. I think it's still not gonna work because proc macro crate, which is used by this, which is used by Solana, etc., uses version 19, not 18. So I might say that this is the thing that should be used, but then if they're not using that, then it's not gonna work. Yeah. So we're not gonna be able to proceed. We're not gonna be able to implement it. Maybe. Let's see. Change the version requirement. Toml edit 0.18. Source. I don't get it. You should find Toml edit. So Toml edit does exist, 19.2, because it's found on crates, 19.2, but eighteen point one. Don't we have 18.1? We do. It's here. So what is its problem? I don't get it. Cargo fails to find great version. Yanking doesn't prevent a version's use, only prevents new crates from depending on it. Let's see if this guy, the package of this guy is available. 0.2.0. It was deleted. Excuse me. So we go back to Toml edit. 0.18 does exist. It hasn't been deleted. But why am I unable to build? Proc macro crate. Okay, so it's here. Cargo. Okay, I just want to know what is actually in the rust up directory, because I'm not entirely sure that's something I should be deleting. Is it safe to delete rust up directory? So saying that I need to is basically reinstall Rust. That's what he's saying. Okay. Let's install it again. So I do have it already. Okay. Okay, have Rust stuff. Okay, now we do cargo build BPF. Hopefully it's getting the indexes correctly now and have no issues. But we'll see. Still not able to find it. Okay, we are stuck. What is my cargo version? interesting reading. It's just not what I need to be reading right now. Failed to select a version for the requirement. Oh, my Solana is actually a lower version. Okay, Solana updated. Solana version updated. Let's exit this bash. Let's do cargo build BPF, and everything should be good, right? Right? I hope. Let's see. It's 4:10 already. I said I'd have to drop off by around 4:15. But let's just see if we can get over this problem. And if things look good, we can just end here. So what have we accomplished today? We read through Paul X's tutorial. We reached up to this point, which is right before we do the deployment, which we can continue next time. Bonus bug fixing. Show first hit, second hit. Yeah, so he did intentionally do it. So he was intentionally testing it. Alright, okay, so that was the error thing that was missing. There's an additional check missing that has to do with the possible states of an account. Didn't check that one. I see. Cool. Okay, let's go back. It is what? It's still building? It's still building. Fine. Let's go check outputs. It's not Rux Analyzer. I think it's just the terminal. You just have to wait for this to complete. Yeah. Okay. So yeah, we passed through it. We were understanding the concept of the escrow and then the logic, right? We learned about we're encountering some new errors now. Oh, it's building. We're encountering some new errors now. Hopefully after we build these dependencies, these things should be okay. Well, we'll see. I'll probably start off with describing the Rust in Solana version was in use. I think it was 1.9 Solana, Rust 1. Can't remember the Rust version, but then we did update everything just to double check if things worked. I think that should be like a common practice at the start of a tutorial, just double checking the environment and stuff. I wonder if the proc macro crate, it was compiled successfully, so it has everything it needed. Okay, that's good. Okay. Almost there. We're doing Solana stuff now. Solana program, okay. And then eventually we will have our escrow program. Right. Solana escrow. So it looks like it's building successfully, which is good. Next session we'll do the deployment and actually check how things actually worked. We'll just let this finish building and we'll close off there. So let's go over my notes just to see the things that we picked up. So I recall traits are basically behaviors that we want to share across different objects, and you need to implement those traits, like what we did in I think it's in Was it? Not this instruction. This instruction. Nope, not this instruction. State. Yeah, states have the implementation for the trait called pack, and yeah, it's for packing and unpacking stuff. Okay, and then attributes or metadata. I think we have one in instruction. I think no. Entry point. No. Processor. Program. Not program. I remember using a macro somewhere here. Oh, it's for the errors, right? It's this one, right? Okay. What else? So we recalled what attributes were. Okay, and then ownership. This is more Rust stuff. References, ampersand. Then cargo features. This is something I haven't read about, so we filed this for reading later. We'll read this together sometime. And we also have the sized trait by Rust, and I don't really know what this is about, so we'll read that too another time. And then Paul gave us some references on what PDAs are from the documentation on Solana, documentation on the Solana program as well under Rust, and the more complicated concepts of cross-program invocation. So just a lot of new things to read about. So I'm quite excited for that. Yeah. It looks like it was able to build everything successfully. Exit 0, no problems, okay. So I would assume there is now a target, and then this would have produced a .so thingamajig. Let's go check the instructions again here. Building the escrow program. I don't think we were here. Here? Build BPF with the SO extension. So let's go check if we have a .so. Looks like we don't. Run Solana keygen, new to create and save, fill up your local network, config, Solana deploy, to deploy the program to local net. The path to the program will have been printed by cargo build BPF. So where is the program? So the program is let's go run it again. It just has warnings. It says it finished. It's under release. Build. Nope. Those are parts. Dependencies, examples, incremental. Temporary. I'm not sure where it is. You can only deploy the program for because we're using file that's not enabled on any cluster yet. Path to your program. So yes, where is my program? The path to the program will have been printed by cargo build BPF. Cargo build BPF. Let's see. Do I have release deploy? There we go. Solana escrow.so. Okay. So it is under deploy or under target. Solana escrow.so. Right? So that's where it is. And then we just need to follow the set of instructions next. So we'll do that next time. Thank you for joining me. Yeah, let's keep learning Solana together. See you guys soon.